Hello students and friends, this is my second session. Now we quickly recap the last session, that was first session held yesterday. We had a discussion about double integrals over the rectangular regions, and the double Riemann sum, it is an approximation to the volume we have discussed, that is the under surface F and the above rectangle R. And volume of a solid that lies above the rectangle R and below the surface Z equal to fxy is expressed as the double integral fxy dA is equal to, it is the limit of the double summation f of xi star yij star into delta A. That is nothing but we added the volumes of all the rectangular columns. We have discretized the entire region into m into n number of sub rectangular regions on the xy plane. Then we took the heights of all the rectangular boxes and multiplied with their areas. Then that m and n are tends to infinity, means we added infinite number of rectangular columns. That leads to the definition of volume. And you can interpret the double integrals as area also. In the special case, if the function fxy is equal to 1 for all the points xy, means it is a constant function. For any x and y, fxy is 1 in the region R. So each term in the Riemann sum is of the form 1 into area, 1 into delta A, that becomes delta A, and the double integral gives the area of that region. That is the interpretation of double integral as an area. To calculate the area of region R, we replace the function, that is the height of the rectangular box is 1. So in the Riemann sum also, if all the rectangular boxes their heights are 1, only we are adding all the areas of base areas of all the rectangular columns. That means the double integration 1 into delta A is nothing but double integration over the R delta A gives the area of the region R. We also discussed in one of the example the volume is approximated by the addition of all the rectangular columns. If you increase more number of rectangular boxes, the volume becomes better approximations. We have seen m and n are 4, the volume gives 41.5, and if you increase m and n equal to 8, there are 64 rectangular boxes, the volume gets 44.87. Still if you increase m and n are 16, means 16 into 16, 256, the volume is approximated to 46. The actual volume of that problem was 48, means if you increase more number of sub-rectangular columns, that gives the exact volume 48. Okay, today in this session we will discuss the how to evaluate the double integrals. We had a discussion about only the Riemann sum. To recall that it is usually difficult to evaluate even a single integrals directly from the definition of an integral, but from the fundamental theorem of calculus, it gives a much easier method. Even the evaluation of double integrals from the first principle is even more difficult. In such cases, we go for the iterated integrals. So in this section, we see how to express a double integral as an iterated integral, which can then be evaluated by calculating two single integrals from the given double integrals, which is then evaluated by integrating two single integrals. Suppose you take fxy be a function of two variables and it is integrable on the region R, which is bounded by the limits x equal to a, x equal to b, and y equal to c, and y equal to d. Again, a, b, c, d are constants, that is a rectangular region. The double integral is written as the integration from a to b, c to d, fxy dy dx. We categorize into different type of regions. the type 1 region, we call it as a rectangular region in the xy plane. That is, if all the limits x equal to a, x equal to b, y equal to c, y equal to d are constants, all the limits are constants, then the integration over the region R fxy dx dy can be written as a to b, another integral c to d fx dy fxy dy into dx. Here the inner integral, that is c to d fx dy, means that x is fixed constant here. With respect to y, we are integrating with respect to y, keeping x is held fixed here, and fxy is integrated with respect to y. The function fxy is integrated with respect to y from y equal to c to y equal to d. This procedure is called the partial integration with respect to y, like how we differentiate partially one with respect to x and with respect to y. In the similar manner, it is called the partial integration with respect to y. After that, now c to d fx dy fxy dy, it is a number which depends on the value of x, because x is fixed while evaluating with respect to y. So, this becomes a function of x. This inner integral, after the integration, this becomes a function of x. We denote it as ax. Ax is equal to c to d fxy dy. That is the inner integral. After the evaluation, that becomes the function of x, because x is fixed constant here, we integrated with respect to y. So, that is ax inner integral. We now integrate the function that ax with respect to x from x equal to a to x equal to b. We get the integral a to b, the inner integral is ax dx, that equal to a to b, the inner integral is c to d fxy dy into dx. This integral on the right hand side is called an iterated integral, means we are integrating one by one, integration with respect to y, then integration with respect to x. This integral is called an iterated integral. Thus, we can write a to b c to d fxy dy dx is equal to a to b is the outer integral, c to d fxy dy, that is the inner integral, into dx, means that we first integrate with respect to y. That means we first integrate with respect to y, that is the inner integral, from the limits y is equal to c to y is equal to d. Then integrate with respect to x from the outer limits a to b. Similarly, the iterated integral can be written in this way also. The same double integral is equal to, we have taken c to d are the outer limits and a to b fxy dx, that is the inner integral. This means that we first integrate with respect to x, that is the inner integral. We first integrate with respect to x from x equal to a to x equal to b. This becomes the function of y. After the integration and substituting the limits, this becomes the function of y, then which is integrated with respect to y using the limits y is equal to c to y is equal to d. The same integral can be written in either of the way. First integration with respect to y, then integration with respect to x, or we can do the integration with respect to x first, then y. Let us see some examples here. To evaluate the problem 0 to 3 and 1 to 2 x square y dy dx. It is given that as per the problem, the dy is the first integration. So, its limits are y is equal to 1 to y is equal to 2. So, I can write the given integral I is equal to 0 to 2, that is the outer integral 0 to 3, and the inner integral 1 to 2 x square y dy then dx. So, the given integral you can write it in this way. Dy is given the first, that is the inner integral. So, integrate with respect to y first here, the outer integral as it is, integrating the inner integral with respect to y. So, while integrating with respect to y, we keep x constant here. So, x square is kept constant, integrating y, that becomes y square by 2, then substitute the limits 1 to 2 dx. So, that is the integration procedure. Now, putting the limits here 0 to 3, put y is equal to, in place of y is equal to 2 and y is equal to 1, that is the lower limit. So, we keep outside x square by 2 is kept constant, put y is equal to 2, 2 into 2, 2 square, that is 4, minus lower limit y is equal to 1, that is 1, then dx. So, that simplifies 4 minus 1, that is 3 by 2 constant, 0 to 3 x square by 2 x square dx. So, I told that the inner integral, after the integration of the inner integral, that is with respect to y, that gives the function of x, that is x square. Now, integrating that with respect to x, 3 by 2, 0 to 2, that is x cube upon 3, x cube upon 3, then put the limits 0 to 3. That simplifies 27 by 2. You can substitute the limits x equal to 3, that is 27 by 3, and x equal to 0. So, 27 by 3, 3 cancels, 27 by 2, that is the value of the iterated integral. One can also use the other way. If I integrate first with respect to x, means the y limits are kept outside, 0 to 3 x square y dx then dy. So, y limits are 1 to 2 and x limits are 0 to 3. Now, integrating with respect to x first, that is keeping y constant. So, 1 to 2 x square becomes x cube upon 3, y is kept constant, and substitute the limits 0 to 3 dy. Now, using the limits in place of x, so 1 by 3 you can take outside, 1 to 2, y is kept constant, substitute in the x, 3 raised to 3, 27 by 3, and y equal to x equal to 0, that is lower limit 0. So, that is the integration with respect to x. Now, integrate with respect to y. So, it simplifies 27 by 9 and 1 to 2 y square into dy. We know the integration of y square, that is y cube upon 3, 27 by 9 into y cube upon 3, 1 to 2. So, that simplifies again 27 by 9, it is 2 raised to 3, 8 by 3 minus 1 by 3, 8 by 3 minus 1 by 3, that gives x equal to 2. The first we have integrated with respect to x, that is x cube upon 3 y as it is, putting x value x equal to 3, that is 27 by 3, x equal to 0, that is 0 minus 0, that is 27 by 3. Now, integrating y square, that is y cube upon 3, 8 by 3 minus 7 by 3 it is 27 by 9 into 7 by 3. We can simplify that 3 into 9 27. So that has to get 27 by 2 the same answer, or we did integration, that is it should come 9y, it is there 9y, it is the simplification 9y it is 9y is 9 you have to get 22 by 7 27 by 2. So if you integrate with respect to x first or y first, that means the order of integration doesn't matter here. So note that we obtain the same answer whether we integrate with respect to y first or x first. The two iterated integrals are equal here. That means the order of the integration doesn't matter. We can do the first integration with respect to x or with respect to y. Both will give the same answers. You take another example, that is 0 to 2 and 1 to 2 x square plus y square dx dy. Here dx is the inner integral, that is integration with respect to x square plus y square dx from the limits 1 to 2. You integrate with respect to x. With respect to x means keeping y constant, so x square into y you will get, then y square integration is y cube by 3. That gives to, putting in place of x the limits 1 to 2, that becomes 7 by 2 plus y square into dy is equal to 22 by 3. This example, the practical method of evaluating the double integrals by expressing it in iterated integrals. There is a theorem, FUBINI'S theorem. It gives you the practical idea how it actually evaluates. We integrate first with respect to x and first then with respect to y, or either of one. This FUBINI'S theorem, we demonstrate the last example. If fxy is a continuous function in the rectangular region R bounded by the limits x equal to a to x equal to b and the limits y equal to c to y equal to d, then if fxy is a positive, we assume the function fxy is a positive, then the double integral can be interpreted as the volume V. Yesterday we discussed the double integral is interpreted as the volume of the solid S that lies above the region, rectangular region R, and the under the surface Z is equal to fxy. Here the double integral fxy dx dy over the region R, where Ax, if you integrate first with respect to y, that gives the function of x, where Ax is, what is the Ax here? Ax is the area of the cross section of the solid S in the plane through x and perpendicular to x. You can see the figure here. From the figure, Ax is the area under the curve C, whose equation is the surface equation Z is equal to fxy, whose equation is the surface equation. C is on the surface, where x is kept constant while integrating with respect to y. X is held constant and y is varied from c to d. See here, Ax is denoted as the inner integral c to d f of xy dy. So that is the plane area. Ax is the plane area where x is fixed here. This is the x axis. X is fixed, held constant. Y is varied. Y is varied from c to y equal to d, that gives the plane area under the curve C. Then the volume is nothing but this plane area is covered the entire x limits. This covers from x equal to a to b, that fills the solid S, that is the volume of the solid under the surface and above the rectangular region. That is the FUBINI'S theorem interpretation. We integrate usually the inner integral, then outer integral. After the inner integral, that is the function of x, means if you integrate with respect to y, that gives the function of x, because x was held constant, that is the plane area under the curve C. C is on the surface here, because x is fixed, y is varied. This area is moved, covered from x equal to a to x equal to b, that gives the volume under the surface. Similarly, the iterated integral, double integral c to d a to b f of x y dx dy. Here c to d ay dy is written. Ay is nothing but the inner integral is integrated with respect to x. The same double integral we can do the first with respect to x or with respect to y. Here the inner integral is integrated with respect to x from a to b, that becomes the function of y, that is denoted as ay. You can see the picture also, ay. So the x axis and y axis here. Here y is kept constant, at some point y is kept constant, x is varies from a to b, x is varies from a to b, that gives the plane area under the curve C. C is on the surface here. How the surface is plotted, and that way the curve is drawn here. So y varies from C to d. Next integration, we extend this area entire the y axis. Entire y axis means entire the y limits, y equal to c to d, that covers the rectangular region a to b and c to d. So ay is written here, that is the first integration with respect to x from x equal to a to b, that is a function of y. Then that function of y is integrated with respect to y from c to d, means that covers the solid S, which is the volume of the solid S. This is the example drawn from the GeoGebra. I can demonstrate the same example using the software. You can see lively, understand the concept, how the volume is generated from this figure. Here the same example, x limits are 0 to 2 and y limits are 1 to 2. The function is x square plus y square dy dx. The inner integral is with respect to y and outer integral is with respect to x. See, the rectangular region is plotted on two-dimensional here, x equal to 0, that is y axis, x equal to 0 to x equal to 2 here, and y equal to 1 to y equal to 2, that is the rectangular region. Now this you can see in the three-dimensional, there is a plane region, you can see it. I told that with respect to integration with respect to y, the plane region is ax, that is a function of x. The green color you can see, that is the plane region under the curve C. There is a curve on the surface, this line is the curve. Ax is a plane region under the curve C, where x is fixed here. This is the x axis, red color, x is fixed and y is varied. Y is varied from C to D. So if I move the strip here, if I move this, you can see that plane area covers the entire x limits, the plane area that covers the entire x limits, so that the volume is generated under the surface. The surface was x square plus y square. This is the cylindrical surface. That is plotted for all x and y, but in the integration it is taken only the rectangular region above that function values. These are the fxy values for those x and y points. So, this is the volume generated under the surface x square plus y square above the rectangular region bounded by x equal to 0 to 2 and y equal to 1 to 2. Okay. Next, these are the examples you can work out. All the limits are constants here, 0 to pi and 0 to pi, 1 to 2 and 3 to 4. There is an option you can integrate first with respect to y or with respect to x. So, accordingly we have to change the limits of integration. We can't change simply dy and dx here. As it is, the dy is given in third example, we have to integrate with respect to y using 3 and 4 limits. If you want to integrate with respect to x, means you bring the limits 1 to 2 are the inner integrals, then dy means the outer integrals are 3 to 4. So, you want to change the order of integration, change the limits of integration accordingly, then get the answers. I take one real life example here. This may be a civil engineering problem, or one can understand here. It is simple real life example. A building is 8 meter wide, it is given, and 16 meter long. It has a flat roof that is 12 meter high. Building is 8 meter wide and 16 meter long. It has a flat roof that is 12 meters high at one corner, 12 meters high at one corner, and 10 meters high at each of the adjacent corners. 10 meters high at each of the adjacent corners. The question is, what is the volume of the building? You may get such problems in real life. What is the volume of the building? Here, if we put the high corner on the z axis, I have taken the high corner on the z axis and long side along y axis and short side along x axis. You can see the picture here. 12 is the maximum height of the building. On the y axis, the long is 16, along x axis 8. It is given the 12 meters, it has a flat roof that is a 12 meter high at one corner that is z axis 12 meter high, and 10 meter high at each of the adjacent corners here along y axis and x axis, the 10 meter height. So, this is the shape of the building as per the specifications are given. So, what first we have to find out what is the equation of the roof. What is the equation of roof? We know the rectangular region here on the xy plane, 16 into 2. X varies from 0 to 8 and y varies from 0 to 16. So, on the roof it is not the parallel to the rectangular region, it is the slanted roof building. The height at the z axis is 12, at the y axis is 10. Now, first we have to identify what is the equation of the roof. Then the roof is a plane region, it is with the z intercept is 12. Intercept means the height of z axis is 12 and the x slope is minus 2 by 8. How it is minus 2 by 8? You can see this side the 10 meter is the height and this side 12 meter is the height. There is a difference of 2 meters. This side it is 12, along z axis side it is 12. So, the difference is 2. You can find 2 is the difference, 2 divided by 8 along x axis 8 meter is there. So, minus is taken because it is the slope at downward. So, minus sign is taken. Minus 2 upon 8, the x slope gives minus 1 by 4, and similarly the y slope gives minus 2 by 16. 16 is along the y axis, minus 2 upon 16. That becomes minus 1 upon 8. Hence, we can form the equation of the roof, that is z is equal to 12 minus 1 by 4x minus 1 by 8y. This is the equation of the root, which is the slanted here, this roof, that is the plane surface. That equation is z is equal to 12 minus, we can verify at all the corners, when x equal to 0, y equal to 0, z is equal to 12. At z axis, the height of the building is 12. Similarly, you can verify at any axis, x axis, y equal to 0, x equal to, you can substitute, you will find the height of the building at x axis and y axis. Now, the volume is nothing but the double integration of the function fxy dx dy. Here the function fxy is z, that is the plane, 12 minus x by 4 y by 8 dx dy. So, this gives the volume of the building which is given in the picture, where R is the rectangular region. From the given dimensions, R is the rectangular region where x varies from 0 to 8 and y varies from 0 to 16. You can see in the picture, x varies from 0 to 8 and y varies from 0 to 16. They are the limits of the rectangular regions. So, the volume is equal to 0 to 16 y limits, 0 to 8 x limits, then the function is substituted dx dy. So, if you integrate this with respect to x first here, dx is given first, integrate with respect to x, that gives, I told you already, that gives the function of y. After the integration, that gives the function of y. In the picture you can see this one is the function of y, So, this plane area, it is the plane area under the curve. This is the curve on the surface, on the roof it is. This is the curve on the roof. So, this is the function of y. If you integrate with respect to x, this is the plane area under the curve, which is the function of y. Then if you integrate with respect to y, means this area is covered the entire base here, entire room. So, we can demonstrate this using the tool here, software GeoGebra. You can understand clearly how it looks, the volume. See, here I entered x lower limits 0 and x upper limits 8, y lower limits 0, y upper limit 16. This is the plane roof, equation of the plane, that is fxy. So, this is the rectangular region in the xy plane, rectangular region in the xy plane it is. Here in this picture, this is 3-dimensional, you can see there is a roof. I can view again 3D picture. You can see here the 3-dimensional picture, and correspondingly we need a 2-dimensional. This is the plane roof, you can see. We have to get parallel both the sides. That red color is not exactly plotted what the roof. Here the below that is the region on the xy plane. If I move this, you can see that plane area, which is a function of y, moved along the x axis, So, you can see, here. Again we have to trace this here, tracing that in 3-dimensional picture the volume is generated. You can see volume, you can see here clearly above the rectangular region, below the plane, the slanted plane, you can see that is plotted for all x and y. We consider below that means above the rectangular region, that is the volume of the building. Z axis, this is the height 12 and it is slanted towards x axis and y axis. So, its volume is given as, if you integrate that, it gives 1280, the volume of the building. So, in this way we can solve any real life examples using the double integrals. Now, coming to the other type of reasons. Now, we have discussed the constant limits and their evaluation. If the limits are constants, the region in the xy plane, you will get a rectangular region or square region. That was the easy to evaluate the integrals using first integration with respect to x, then with respect to y, or vice versa. Now, the another type of region, here the y limits are functions of x. Y limits are functions of x. They are y is equal to say g1x and g2x, they are functions of x, and x limits are constants. Take a and b are the constants. If you plot them roughly, the graph, you can see y is equal to the one curve g1x and y is equal to g2x is another curve, and x equal to a constant, it is a line, and x equal to b. So, between a and b, the two curves is taken, y equal to g1x and y equal to g2x. They may be any fashion. Here y is equal to g1x and y equal to g2x, where x limits are constants a to b. Next, to evaluate such regions, they are of type 2. The double integral over the region R fxy dx dy is equal to, taking the constant limits as the outer integrals x equal to a and x equal to b, and the inner integral contains the variable limits y is equal to g1x, y equal to g2x, f of xy dy, then dx. So, we have to consider the variable limits as the inner integral limits and the constant limits are the outer integral limits. Here the inner integral y is equal to g1 and y equal to g2 fxy dy, it is first evaluated the integration with respect to y. It is first evaluated with respect to y, which becomes, I told you already, which becomes the function of x. Once you integrate with respect to y, then substituting the limits, you will get which is a function of x, that is ax. Then the integrate that ax is a function of x, integrate ax from the x limits, x equal to a to x equal to b. That is the evaluation of type 2 region. Similarly, there is another type, we call it as type 3 region. If x limits are functions of y, here x limits are functions of y, you can call it as x equal to h1 of y, x equal to h2 of y, and y limits are constants. Y limits are say c and d are constants. Such regions we call it as type 3 regions. You can see the diagrams here. x is equal to h1 of y, that is a function of y, and x equal to h2 of y is another function of y. It is integrated between the constants c, y equal to c and y equal to d. They may be any fashion, the curves may be in any fashion, x equal to h1y, x equal to h2y, and limits not necessarily the positive limits, y is equal to c and y equal to d. So, such reasons are type 3 reasons. Now, in that type 3 reason, first we evaluate the inner integral that is with respect to x, using the x limits, they are functions of y, x equal to h1y, x equal to h2y. That is integrated first with respect to x, which becomes the function of y. Once you integrate with respect to x, that becomes the function of y, that is ay. Then integrate that function of y with respect to y from the constant limits c to d, that gives the evaluation of the iterated integral of type 3. There is a property the integration of a constant function over the region d gives the area of d. As I already discussed, the function f(x,y) is 1, then the double integral 1 into dx dy gives the area of the particular region d. Is this the area, is the question. Function is 1 means height of the solid is 1 here. Height of the solid is 1, just we have added the dx dy, area of the rectangular region, which gives the area of the region in D. Now we consider the examples on type 2 and type 3 as we discussed here. This is an example of type 2. You can easily recognize when the limits you can observe here, one set of limits are constants, another set of limits are functions of x. That means it is of type 2. That is, x limits are constants, x equal to 0 to 1, they are constants, and y limits are functions of x. Whenever the limits are in terms of x, you consider them as the y limits. Y is equal to 0 to x square. Then the function is given x plus 2y dy dx. So, we know that how to evaluate the type 2 iterated integrals. That you consider the limits x equal to 0 to 1, they are the outer limits, and the inner limits are y equal to 0 to y equal to x square. Then integrate x plus 2y with respect to y, x plus 2y with respect to y. So, the integration of the inner integral with respect to y means keeping x constant here, keeping x constant. You can do here simplification. The integral given as 0 to 1, x equal to 0 to 1 outer limits, and y equal to 0 to x square, they are y limits. The integrand is x plus 2y dy then dx. So, first integrate the inner integral with respect to y. Now, the x limits are same, integration with respect to y, keeping the variable x constant here, x constant, then x into 1 it is, 1 integration is y plus 2y integration with respect to y, 2y integration is 2 into y square by 2, that is the y square differentiation is 2y, the integration of 2y is y square. Then put the limits 0 to x square. Now, substituting the limits 0 to 1 as it is, in place of y we substitute x as it is, in place of y it is x square upper limit. I substitute here lower limit y is equal to 0, that is 0, means x as it is, putting in place of y is equal to x square, that is upper limit, minus y equal to 0, the lower limit. Go for the second term, put y is equal to x square, it is y square. So, x square raised to square, x raised to 4 minus y equal to 0, 0 it is. So, that completes the inner integral. Now, simplify here, 0 to 1, it is x cube plus x raised to 4 dx. So, after the integration with respect to y, that becomes a function of x. It should not contain the y terms here. It is a function of x. Next, integrate this, x cube integration, x raised to 4 by 4, x raised to 4 integration, x raised to 5 by 5, 0 to 1. Simplify that, putting x equal to 1, that is 1 by 4, 1 by 4 plus 1 by 5, the lower limit is 0, you will get 0 there. So, adding these two, 20 is the LCM, 20 is the LCM. So, numerator you get 5 plus 4, that is 9. So, the value of this iterated integral is 9 by 20. Again my question is this number what represents? What is the representation of 9 by 20? I can also demonstrate the same with GeoGebra. Any problem you can demonstrate here. You can see what it represents graphically. Here I have taken x limits 0 to 2 and y limits 1 to x square. X square is a parabola, you can see here, x square is a parabola, and x equal to 0, that is a y axis, one boundary, x equal to 1 is the other boundary. So, this is the region R in the xy plane. You can see the corresponding figure in the 3-dimensional here. So, this plane is nothing but the that you have to change here, that is x square plus y square. It was taken x plus 2y. If I change x square plus y square, x square plus y square, that is the cylindrical surface, you can see cylindrical surface. So, under that you can find the volume here. So, after the integration you can see the plane region there, plane region. This plane is the function of x under the curve C. Now, if I move that plane region over the entire x limits, plane region over the entire x limits, so it covers the total region in the xy plane. Similarly, you can see the generated solid figure you can see how the region in the xy plane, according to that the solid is generated here. Earlier problem it was rectangle, now it is not a rectangle, there is a parabola here, there is a parabola, and this side is a line, straight line. So, below that this is generated, that is the volume, green color you can see the volume. Even you can move and see the volume generated under the surface x square plus y square. So, every example you can see how that volume, only when it is the volume, whenever the function is positive, whenever the function is positive, then whenever the function is positive, then the value you obtained after the integral is 9 by 20. So, in this problem x plus 2y was taken, I took this one different function. You can plot any function there, here x plus 2y, that is it is there, x plus 2y. The same example, there is a x plus 2y is the plane in the 3-dimensional. X plus 2y is a plane in the 3-dimensional. See that x plus 2y is a plane region in through 3-dimensional. Below that, that is generated. I can see, move that. If you cover that plane, entire region in the xy plane, and simultaneously you can see the solid generated below the surface. Surface is a plane. Surface is a plane here. Okay. So you can change any function, integrand, and see the volume generated here. So 9/10 is the volume because the function x plus 2y is a positive. If x plus 2y, that is fxy, is not positive, we cannot say that this is the volume. Just it is a number, is the value obtained after the integration. When this is a positive quantity, that value is represents the volume of the solid under the surface. Similarly, there are many examples you can see here. Find the volume of a solid that lies under the paraboloid, the same example x square plus y square, and above the region R in the xy plane is bounded by the line y is equal to x and the parabola. Here both y limits are functions of x here. First we need to find out the x limits, y limits are given here. What are the x limits? To find the region R, solve these two equations, y is equal to x and y equal to x square. Solving these two, we get the points of intersection, y equal to x and y equal to x square. If you solve these two, you will get the point of intersection, y is equal to x and y equal to x square. Substitute one another, you will get x is equal to x square, or x square minus x equal to 0, or x minus 1 is equal to 0. That means x equal to 0 and x is equal to 1. These are the x limits. For x equal to 0, if you substitute in both the equations, you will find y equal to 0. And x equal to 1, if you substitute in both the equations, y is equal to 1. That means the points of intersection for those two curves are 0, 0 and 1, 1. In the figure, you can easily plot both the points where we got x limits are 0 to 1 and y limits are this. You can see the figure. Y equal to x square and y equal to x is a line, y equal to x square is a parabola, and x limits are 0 and is equal to 1 here. So this is the point of intersection 1, 1. So after the integration, as usual you know how to integrate this. First integrate with respect to y using the y limits, and integrate with respect to x using the x limits 9/105. So this is the graph you can see here. This is the cylindrical surface, z is equal to x square plus y square. You can demonstrate lively plotting the region in the xy plane and corresponding the volume generated here. So this is the region in the xy plane. The downward curve is y equal to x square. The above curve is y is equal to x. Correspondingly in a 3-dimensional, you can see there is a 2-dimensional region and also 3-dimensional in both of diagrams in one picture. If I move that plane area covering entire x limits, x equal to 0 to 1, x equal to 0 to 1, this gives the volume you can see under the surface z is equal to x square plus y square above the region bounded by two parabolas between x equal to 0 to x equal to 1. So that green color is the solid, that gives the volume of the solid above the region that is bounded by the two parabolas, and below the given surface. So, that is the interpretation of the volume you can understand seeing this 3-dimensional graph. So, thank you. This is the end of the session.